Hello, welcome to another session on math for data sciences. So till now we have been looking at a lot of properties for exponential distribution. So we looked at expected value, which is the mean of the distribution computed as 1 upon mu. Then we looked at the second movement of the distribution, which is expected value of x square, and it is computed as 2 upon lambda square. And then using these two values, we were able to get the variance as 1 upon lambda square. Then we looked at how we define the nth movement of a distribution. It is nothing but the expected value of x raised to power n. So just like we computed mean as e expected value of x, that is the first movement of the distribution, and similarly expected value of x square was 2 upon lambda square, that was the second movement of the distribution. Then we looked at how we can compute the central movements of a distribution. It is nothing but it is computed as the expected value of x minus mean whole raised to power n. And we looked at how we can compute the first and the second central movement of the distribution. We saw that for the first movement, the value of the central movement, first central movement is always equal to 0 irrespective of the distribution, because expected value of x is equal to mu, therefore this comes out to be 0. Then we also looked at the memoryless property of exponential distribution, where we saw the probability of waiting for a particular, we saw an example of a bus stop where we saw that the probability of waiting for a bus, given that the waiting time has already been k minutes, the probability of waiting another x minutes still remains the same as the initial probability of waiting for x minutes. So this means that the distribution of waiting time does not change given that there has already been some k minutes which have passed. So the conditional distribution still remains the same as the original distribution, which was the exponential distribution with the same parameter lambda. Then we had also looked at Tukey criteria to get outliers, limits for the outliers, and what we saw is we got the first and the third quartile, which was as given here, and then using the difference between the first and the third quartile, we got the IQR, which was the interquartile range. Now, according to the Tukey criterion, we saw that any value of the random variable which is less than q1 minus 1.5 times IQR, that would be considered as an outlier on the from the left side of the distribution. Now, one thing to note here is when we calculate q1 minus 1.5 into IQR, we notice that this particular value is actually less than 0. But since we know that exponential distribution was defined for x greater than 0, therefore there would be no outlier on the left side of the distribution. So there will be outlier on the right side of the distribution using this particular relation, but there is no outlier in this distribution which is on the left side of this distribution. So the outlier in this case will only come from the right side of the distribution, where the value of x is greater than log of 4 plus 1.5 times log of 3 whole divided by the lambda, which is the parameter of the distribution. So this was the Tukey criterion. Now next, the new topic which we'll be looking here would be mode of the distribution. Now the mode of the distribution is defined as the most frequent value of the distribution. Now since this is the most frequent value, what we want to do is we would want to maximize the probability of that value to occur. So most frequent value means it occur most number of times, and therefore the probability of occurrence of that value should be maximized. And we want to, so to maximize the probability, we would want to maximize the PDF of the distribution. Now for exponential distribution, so let us say we have an exponential distribution here with parameter lambda. We already know the PDF is given as lambda e to the power minus lambda x for x greater than 0. Now we also know e is approximately equal to 2.71. Now fx could be written as lambda divided by e to the power minus lambda x. Now since e is greater than 1, therefore e to the power minus lambda x would always be greater than 1 as well, irrespective of the value of lambda and x, given that x is greater than 0. We already know x is greater than 0. Therefore, e to the power minus lambda x would always be greater than 1, because anything raised to power 2.71 would always be greater than 1. To get a value less than 1, we would have to have this base value as less than 1, which is not the case here. Now, since e to the power minus lambda x is greater than 1, therefore 1 upon e to the power minus lambda x would be less than 1. Therefore, fx always decreases with an increase in x. Now, this particular property of exponential distribution makes it a monotonically decreasing distribution. So what does a monotonically decreasing distribution means? It means if x2 is greater than x1, then fx2 has to be always less than f of x1, which is the case here, because as we keep on increasing the value of x, the value of fx always decreases. Therefore, the PDF of the given distribution would have a shape which is monotonically decreasing, and it would be given something like this. And this is the probability density curve for a exponential distribution, or PDF for an exponential distribution. Now, since the value of PDF is always decreasing, the maximum value of PDF is actually obtained at x equal to 0, because we know that x is always greater than 0. So for exponential distribution, maximum value is achieved at x equal to 0, because for every value of x greater than 0, the value of PDF would be less than f of 0. Therefore, the mode value is given as f of 0, which is lambda. This is the required mode of the distribution. So this is not so the mode of the distribution is the value of x at which the maximum value is achieved. So the mode of the distribution is 0, but the value of the PDF at the mode, which is f of 0, is equal to lambda. So this is actually the probability density value. So one has to remember here that the value of the mode itself for the distribution is 0, because mode is the x value of x at which the maximum value of PDF is achieved, and the maximum value of PDF achieved is equal to lambda here. So this is how we get the mode of exponential distribution. And in general, for any distribution, if we are looking to get the mode, we need to find the maximum value of the PDF, and we need to find the value of x at which that maximum value is achieved. That value of x would be the mode of the distribution. So now this is regarding the mode. Next, what we'll be looking at is something called skewness of a particular distribution. Now, skewness of a distribution is a measure of, skewness is a measure of asymmetry around its mean. So skewness is defined as the measure of asymmetry of the distribution about its mean. Now, skewness mathematically is computed as the third standardized moment of the distribution. Okay, so now before moving to deriving the skewness of exponential distribution, what we'll be looking at is these three charts here. So since we are defining skewness as the measure of asymmetry about its mean, we first take an example of a normal distribution, that is the middle graph here. So a normal distribution, which actually we'll be looking in more detail in later sessions, but just to explain skewness here, a normal distribution is a kind of distribution that is symmetric about its center. So as we can see, if we go towards the left of the center and right of the center, the distribution is exactly equal to each other. And since this is the peak here, so the max PDF value is achieved here, and therefore this is the mode of the distribution as well. And since this is the middle value, this is the median of the distribution as well. And since the distribution is symmetric about this particular value, therefore the mean would also come in the middle, and therefore for a normal distribution, all three central measures of tendency, which is mean, median and mode, are equal to each other. So this is the normal distribution, and since it is very symmetric and skewness is a measure of asymmetry, therefore the skewness of a normal distribution is always equal to 0, since there is no asymmetry in this particular kind of a distribution. Now if we look at the left one here, which is an example of a left skewed distribution, we see that there is a tail on the left side in this particular distribution. Now just to remember whether a distribution is left or right skewed, the best way to look at it is whenever you see a tail on the left side, it's a left side distribution. So there's a longer tail on the left side for a left skewed distribution, and there is a longer tail on the right side for the right skewed distribution. So this is how we define the skewness of a distribution, which explains the measure of asymmetry in the distribution. Now in financial applications, left skewed distribution could be more relevant because it denotes that there is a higher chance of rare and large losses than one would expect from a historical data. So that is why to model anything in terms of, for example, a returns of a particular market index, we normally should use left skewed kind of a distribution to denote that there is always a good chance of a higher loss than expected from a normal kind of a distribution. So in financial applications, we should normally stick with the left skewed distribution to explain the returns of a market index to give the riskiness of that particular investment. So this is about right and left skewed distribution. Now we'll come back to exponential distribution, and we'll try to find mathematically what is the skewness of an exponential distribution. Now for exponential distributions, we know that so we have to find the third standardized movement of the distribution, and this is computed as the expected value of x minus mu whole cube divided by sigma cube. So we know that sigma square is variance, and we know that sigma square is 1 upon lambda square as we have derived before. Therefore sigma cube we already know would be 1 upon sigma cube. Now the numerator here is actually nothing but the third central movement of the distribution. So if you remember, we had looked at central movement in the previous session, where we had derived the central movement for the first and second central movement for the exponential distribution, but here we do need the third central movement of the exponential distribution. So how we do that? We first expand the x minus mu whole cube. So we calculate the numerator here. This is given as e expected value of x cube minus mu cube minus 3x square mu plus 3x mu square. Why is that? Because we use the algebraic identity a minus b whole cube is given as a cube minus b cube minus 3a square b plus 3ab square. So that is what we used here to expand this expected value operation. Now we can bring the constants out of the operator, and we can keep the variables inside. So this will become expected value of x cube minus mu cube. So expected value of a constant is same as constant. So mu cube is a constant here, and we already know from our previous sessions that mu is equal to 1 upon lambda. So we'll again be using it in this particular case. And then we are left with minus 3 mu expected value of x square plus 3 mu square expected value of x. Now expected value of x is mu, therefore this also become 3 mu cube. Now this 3 mu cube minus mu cube we have here, we can simplify this as expected value of x cube plus 2 mu cube minus 3 mu expected value of x square. Now again, from our previous sessions, we already know expected value of x square is given as 2 upon lambda square. Therefore, we already know this particular term and this particular term. We only need to calculate this. So the expected value of x cube, we'll be calculating using the same process we followed to calculate the expected value of x square. So we'll be integrating x cube into fx, which is lambda e to the power minus lambda x dx. We use the product rule of integration like we have used before. So we write x cube as it is. The integral of lambda e to the power minus lambda x is minus e to the power minus lambda x, and we put the limits 0 to infinity minus 0 to infinity. The derivative of x cube is 3x square. So I am using the product rule of integration here. This was covered in our previous one of our previous sessions. So if you want to go back to that, you can go back to check how we are calculating the integral here. Then for lambda e to the power minus lambda x, we again have the integral given as e to the power minus lambda x with a negative sign. So negative negative becomes plus here, and we are left with this expression. Now once again, the first integral here is x equal to 0. So therefore x cube is 0. So therefore the integral becomes 0 at x equal to 0. Then for x equal to infinity, the e to the power minus lambda x becomes 0 because e to the power minus infinity becomes 0, and therefore we are only left with the second part of the integral, which is 0 to infinity x square e to the power minus lambda x dx. Now if we divide and multiply the given integral by lambda, we would be left with 3 upon lambda 0 to infinity x square lambda e to the power minus lambda x dx. Now the integral which we are left here is nothing but expected value of x square, which we already know is equal to 2 upon lambda square. Therefore we are left with 3 upon lambda into 2 upon lambda square, which is 6 upon lambda cube. So we now have the expected value of x cube here. So this is the expected value of x cube. Now going back to our previous expression, we need to put this value in this expression here. So we do that, we put 6 upon lambda cube, and then we have plus 2 mu cube. Mu is 1 upon lambda, so this becomes 2 upon lambda cube minus 3 upon lambda into 2 upon lambda square, because 3 mu into expected value of x square. So 3 mu is 3 upon lambda, and then expected value of x square is 2 upon lambda square. So we are left with 2 upon lambda cube. This is the third central movement. So this is the third central movement of the exponential distribution. Now that we have the third central movement, we can simply divide it by sigma cube to get the skewness. So we can write it here. The third central movement is given as 2 upon lambda cube. So we have 2 upon lambda cube, and sigma cube we already know is 1 upon lambda cube. Therefore we are left with the value 2. So the skewness of an exponential distribution is given as 2, which is a positive value here. Therefore we have a right skewed kind of a distribution for an exponential distribution, and we have seen that before as well. So if you remember in our previous when we were calculating the mode, we looked at the shape of the distribution as something like this. which just shows the same thing, that there's a right tail here, which means positive skew. So exponential distribution has a skewness value of constant 2. So note that the skewness value is independent of the parameter of the distribution. The skewness of an exponential distribution is always equal to 2, and it is a right tail distribution since it's a positive skewed value. As you can see, we have got the value as 2 here. So this is how we define the skewness, and this is how we derive the skewness for any distribution, and specifically for exponential distribution we have got the skewness value here as 2. Next we would be looking at another concept. It is another higher movement for the distribution. So this is called the kurtosis of a distribution, and just like skewness was the measure of asymmetry, this describes the tailedness or peakedness of the distribution. So oftentimes you would see kurtosis being described as the peakedness of the distribution, but that is not exactly true. It actually gives you the relative difference between the tail and peaks of the distribution, like how much data is basically stored in the tail of the distribution and how much is stored in the peak of the distribution. Now there are three types of kurtosis. Just like we had three kinds of distribution in terms of skewness, we have three kinds of distribution in terms of their kurtosis values as well. So for leptokurtic distribution, as we can see from the top distribution here in blue color, so this particular distribution, leptokurtic distribution clearly has got heavy tails and it has sharp peak. So clearly, since this particular width here is lower, therefore there is a sharp peak which is visible here, and as you can see, the height of the blue curve here is max height for leptokurtic, and therefore that is why we said that the tails are on the heavier side and this is a sharp peak distribution. Then let's go towards the platykurtic distribution. So platykurtic distribution is the red one distribution here. So clearly it has light tails, as the tails have the lowest height out of the three kinds of distribution here, and there is a flatter peak here. As one can see, it is almost like a flat peak here. Almost the bell shape is actually almost gone, and therefore there are fewer extreme values here. So the fewer extreme values here are there because the tails are light, so there are not many outlier or not many extreme values both on the left and the right side. Therefore there are fewer extreme values. But for the leptokurtic distribution which we saw here, it has heavy tails and sharp peak, and since it has heavy tails, therefore there are more outliers here. So these are more prone to outliers. Now this mesokurtic distribution, this is like a benchmark. So this is like a benchmark, and this is for a normal distribution. So a normal distribution shape, which is a bell curve shape, it has a mesokurtic kurtosis, and the kurtosis value itself for a normal distribution is not actually equal to 0, it is equal to 3. And for leptokurtic distribution, the kurtosis value is greater than 3, and for platykurtic distribution, the kurtosis value is less than 3. Now there is another term which is normally used to denote the kurtosis of a distribution, that is called excess kurtosis. So this is nothing but this is kurtosis for a distribution in excess to 3, and therefore it is computed as k minus 3. So for leptokurtic distribution, excess kurtosis is greater than 0, and for platykurtic distribution, the excess kurtosis would be less than 0. So this is how we define the kurtosis of a distribution. It is the measure of the tailedness or peakedness of the distribution. Now, similar to skewness, we can also compute the kurtosis of a distribution as expected value of x minus mu raised to power 4 divided by sigma 4. Now, this is again the fourth central moment of the distribution. So this will become a little complex computations. Therefore, we will not be really going through the computations here, but the value of kurtosis for an exponential distribution is actually equal to 9, and therefore the excess kurtosis for a exponential distribution comes out to be 6. So excess kurtosis is 6 because it's 9 minus 3, 6. Therefore, exponential distribution is leptokurtic. And finally, we also wanted to define a particular term here. So as you see, when I was defining the skewness of the distribution, I wrote it is mathematically defined as the third standardized movement of the distribution. So whenever we use the word standardized, it normally means that we are normalizing it somehow, and how we are doing it is normally we subtract the mean and we divide it by the standard deviation. So the standardization part will become more clear when we are actually looking into normal distribution. So in that particular session, we'll be going to towards how we can standardize particular values in the distribution. But just to like have a sense of it, whenever we are said to have a standardized value, we just subtract the mean and divide it by the standard deviation of that distribution, and it is also called normalizing the values. But in this case, since we are calculating a movement, that is the expected value, therefore it is called the third standardized movement of the distribution. So third represents the power of the difference in the expected value which we are calculating here. And similarly, kurtosis is calculated as the fourth central movement, fourth standardized movement of the distribution, since we again are dividing the whole thing by the fourth power of the standard deviation of the distribution. So this is about the skewness and kurtosis of the distribution, which gives a good idea about the shape of the distribution without looking at the graph for the distribution. So if someone has given us the skewness value and the kurtosis value of the distribution, we can get a very good idea about the shape of the distribution in terms of how much data is there, more towards tail or less towards tail, as well as what is the length of the tails in both right and the left direction. So this is how we define the skewness and kurtosis. This is it from this particular session.